All right, well, good morning. Last time we met, the very last thing we did in class was to do a calculation on night sky radiation. We almost got through it. I think you're probably good to go, but just in case, I wanted to give you a little bit more background on that. So, first of all, night sky radiation, just talking about that. Now, that is the idea that, how does our Earth cool off, or how do surfaces cool off? If you got any surface at night, it's cooling off by radiating energy out. So it's radiating energy out and cooling. One thing I'd like you to understand is that if you have some surface, its temperature at night can fall below the air temperature. So let's take an example. If the air were 65 degrees Fahrenheit on a summer Sacramento night, you can go outside and check something like the sidewalk or grass or anything like that, and at the end of the night, as you get to around 4 a.m. or something like that, this surface is going to be cooler than 65. And again, that's that radiation going on all night. Maybe a typical case would be something like 58 degrees Fahrenheit. And if you think about that from a heat transfer perspective, we've got radiation going on out, and convection is a heat transfer between a fluid and a surface, so there'd be convection going in. And that radiation going out is bigger than the convection in, so we can get below, our surface temperature can get below the air temperature. Well, how low can it be? It's kind of interesting that there are some societies out there, some indigenous societies, that one ritual that they had was freezing water at night. And you can do that yourself. During the summer, freeze water at night. What you need to do, takes a little bit of work, but if you have a pan, a shallow pan, and you insulate it well around the outside, all night long that water is going to radiate out, and the incoming energy would be convection, and then there's another incoming energy as well, but that incoming energy can be small enough that this water can drop down to, say, 30 degrees Fahrenheit, and you can end up getting freezing. All right, how does that relate to HVAC? Well, there are several applications out there where people have taken advantage of night sky radiation to provide cooling to buildings, and that's basically our last topic of the semester. I wanted to introduce you to those calculations. So let's go ahead and do a similar example to what I did in class, and hopefully that'll clarify how those calculations go. So give me just a second here. So what I want to do is take a look at an example where a radiator is cooled off somewhat. So give me a second. I'm going to imagine a radiator on the roof. I'm going to do it black. A lot of these radiators are black in color because black surfaces radiate well. So I'm going to say it's gotten down to 70 degrees Fahrenheit at night, and it's a surface that has emissivity 0.9, and it's gray. And then the surrounding air, we're going to have it a bit cooler. We're going to have it 60 degrees Fahrenheit. And finally, we're going to have its relative humidity be 70%. Okay, so there's a situation where we would like you to be able to do some calculations. Hey, I got this surface at 70 degrees Fahrenheit. Maybe this surface is a radiator that has water inside it. So there's water underneath here, and we're pulling energy out of that water by radiation. Okay, the air is 60 degrees Fahrenheit. The convective heat transfer coefficient between the air and surface is 1, and its relative humidity is 70%. Okay, so how much cooling are we going to get? Well, the first part is really pretty simple. The first part is just to basically use your emission and to figure out what's going on. So let me get that up there really quickly. Okay, so on a square foot basis, this is something that we did earlier in the semester. Radiation coming out of a surface, you take that sigma, you multiply it by the surface temperature to the fourth, and that surface temperature needs to be in absolute units. So in this case, it would be 70 plus 460, so Rankine to the fourth power. And I encourage you, while I write this down, to see if you can pull out your calculator and do this calculation. 0.9 times sigma, which is 0.1713 times 10 to the negative 8, times the surface temperature, which is this 70 degrees Fahrenheit, to the fourth, and see what you get. So I'll try it myself. I did it earlier. Hopefully you're trying it yourself. Okay, so that's pretty good. 121.6 BTH squared per foot squared out. And you could get that cooling just by doing nothing, just by having water up on the roof. So, for example, if you had a 100 square foot radiator, that would be what? Move this decimal place over 2. 12,160 BTH of cooling just from putting water up on the roof. Okay, it turns out it's not that good because that was a heat transfer going out, but it turns out that in this situation, there might be other heat transfers going on. So let's take a look at convection. Okay, in this case, the surface is 70 and the surrounding air is 60, so that would be out as well. So that's even looking better in this case. So this was emission, and then we also got our convection going on. So quick reminder on how you do that calculation for convection. Give me just a second to write that down. Okay, the rate of convection between a surface and a surrounding fluid, which in this case is air, is the heat transfer coefficient times the surface temperature minus the fluid temperature. And I made the math really easy in this case. The H value is low, which hopefully is the case when you get good cooling at night. And I'll explain a little bit more about that later, or you'll figure that out from some calculations. And the surface is 70. The air temperature is 60. So that's going to be another 10 BTH per foot squared out. Okay, so our cooling rate would be a total of these two, and that looks really good. Okay, then when people actually, take a look at this phenomenon and are saying, hey, is there any way we can take advantage of it? They always found that they got less cooling than these numbers, less cooling than would be predicted. So what's going on? Well, what's going on clearly is that there's going to be radiation coming in. Even if you place something on the roof where there's nothing above it, there's nothing above it. Well, in reality, there is something above it. There's the air molecules above it, and even gases radiate. So trying to figure out what value this is right here. What is G? What is the incoming radiation? Is a pretty perplexing question. I mean, imagine you've got all these air molecules, nitrogen, oxygen, water vapor, etc. How are you supposed to figure that out? Well, people came up with an empirical relation and tried to relate it to something that we did earlier in the semester. So give me a second to do a quick drawing, and I'll get that relationship up there. Okay, so what is known from basic heat transfer is there's an easy equation for this. If you have a small object surrounded by another surface, okay, and you can figure out the irradiation of that small object by using a formula we went over earlier in the semester. G is equal to sigma times the temperature of the surroundings to the fourth. Temperature of the surrounding to the fourth. So people had the idea, well, maybe what we could do is we could visualize this process of a small surface cooling at night. We could visualize the irradiation as coming from a dome and visualize the sky as a dome, and then come up with a temperature for that sky. And so our irradiation would be sigma times T sky to the fourth. T sky to the fourth. Okay, how to come up with the temperature of the sky? Well, it would be in a temperature that would give us the correct radiation. This radiation turned out was not that large, but was significant. So it likely would be a fairly low temperature. And it turns out that the sky temperature in general is lower than the air temperature. So if you had some air temperature, like in my previous example at 60 degrees Fahrenheit, the sky temperature, the temperature of the sky dome, is said to be lower than 60 degrees Fahrenheit. How much lower? Well, that is that formula I put up on the board. So let me write that down for just a second. I know you have it in your notes, but it is, like I said, our last formula of the year. Okay, so there it is. The sky temperature is a fraction of the air temperature, and that fraction is about 70% of the air temperature, but it's adjusted for the fact that one of the main gases in the sky that radiates is water vapor. So there's water vapor out there in the sky. It radiates. The more water vapor, the more radiation coming down from the sky, and that adjusts our sky temperature upwards. So T sky equals T air plus this whole adjustment factor. These two in this formula are in Kelvin. And the dew point in this equation is in degrees C. All right, so it's really a matter of plug and chug. Let me just take you through the example that we just had before. I made the air temperature 60 degrees Fahrenheit, and its relative humidity was 70%. Okay. So what would the equivalent sky temperature be like? Okay, so in a sense, what you're imagining is that you're outside and it's 60 degrees Fahrenheit and the relative humidity is 0.7. The sky is like a heat sink of cool temperature that results in cooling. Okay, well, you just got to do the conversion. So let me get those up there really quickly. Well, actually, a little bit more than that. You also need to go to the site chart. But for these conditions here, okay, I get an air temperature of 15.56 degrees C, 15.56 degrees C. So, on your equation sheet for test 2, have the conversion from Fahrenheit to Celsius. That's a good thing as an engineer to be able to do and be able to do quickly. Okay, how about the dew point? Okay, well, you get that from the psych chart. And from this, you're going to bring a psych chart to our test 2. And for 60 degree air with relative humidity 70%, the dew point is about 50 degrees Fahrenheit, and that converts to 10 degrees C. Okay, so there's all the data that you need to do that. As we did in class, I think the first thing to do is pull out your calculator and work out this adjustment. Work out that whole bracket. So if you did 0.711 plus 0.0056 times 10, that's the dew point, plus this last minor factor here, it turns out that that whole adjustment, and I'll write it up here, the bracket equals 0.7743. Okay, and then if you go through and get the sky temperature, well, the sky temperature, we're using that calculation, is, depending on how precise you are with your Kelvin conversions, 270.8 Kelvin. The sky temperature is 270.8 Kelvin. And then if you convert that to Celsius, well, that's below 0 degrees Celsius. So the sky is essentially kind of like a freezing source. And finally, if you convert that to Fahrenheit, the sky temperature is 28.1 degrees Fahrenheit. 28.1 degrees Fahrenheit. So the way that some engineers or physicists think about this is that all night long, I've got this surface and it's radiating out to some very cold heat sink and resulting in cooling. Okay, so putting it all together, what I'd like you to be able to do is for a surface like this, get the heat out. We did that already. That was 121.6 BTH per foot squared. Get any convection relationships, in this case was out. That was 10 BTH per foot squared. And then finally, get the radiation in. How big is this radiation coming in here like this, and how much actually gets into it? So let me do that last calculation for you, and that should do it. Give me a second, please. Okay, so what we're going to do to get the irradiation coming in, we're just going to do sigma times T to the sky to the force. So that would be G is equal to sigma. The sky temperature we came up, which was about 28.1. So you would add 460 to that, and you get 488.1 Rankine to the fourth. And then I plugged through this myself, and I got 92.2 BTH per foot squared. Okay, so that is actually this number here that's coming in, okay, and but how much actually gets absorbed. So the absorbed is equal to alpha times the incoming radiation. All right? And for a gray surface, I said the surface emissivity was 0.9. And for a gray surface, the absorptivity and the emissivity are the same. So we would do 0.9 absorptivity times our incoming radiation, 92.2, right? And that cranks out to 87.5 BTH per foot squared in. Okay, and that does it then. What you're able to do is combine this number with the two outs, which were 121.6 and 10, and get a net radiation in. So the net radiation in would be equal to 121.6 out plus 10 out minus 87.5 in. Okay, and you can get you'll get some sort of net cooling when you crank through that. Finally, hey, what happens is that what would happen in this case? This is set 60 and this is 70. Well, there's more out. This is going to cool down, and what's done with these systems is the water in there continues to cool, and it will cool 70, 65, 64, 63, 62, 61, 60. When it gets to be 60, the convection is no longer in or out, but you'll see if you go on and do the second part of the homework problem, is that this is actually going to cool below 60, so it might get down to, say, 58. And in that case, it's still going to radiate out, there's still radiation, there's convection in, and it will keep falling in temperature until the radiation out is balanced by the radiation in plus the convection in. And many times in theory, that's a really low number. That's going to be something like in the 40s. And it turns out that people haven't been able to do that. But the practitioners out there who have designed buildings that use night sky radiation, they've usually been able to get the water minimum low 60s and often a bit below the ambient temperature, so down into the high 50s. And 55-degree water is pretty good for doing building chilling, particularly if you have some sort of like radiant floor surface or radiant panel of some sort. Okay, that's it. A couple of you have emailed me and say, hey, when are homework number 8 solutions going to be posted? And that should be pretty soon. I do have a couple other finals on Monday, so I want to get those done. That's coming, but you do have the solutions to number 5, 6, and 7. So make sure you're straightening all those issues out. Please email with me any questions, and we'll see you next week. Take care.